There is a pipe material so hard it scores 9 on the Mohs hardness scale. It does not corrode. It does not leach chemicals. It does not degrade over time. Babylonian engineers installed it 6,000 years ago. Your home has thin-walled PVC instead. We did not abandon vitrified clay because it failed. We abandoned it because a pipe that never needs replacing does not generate revenue. A drainage system that outlasts civilizations does not sell repair fittings. This is the story of vitrified clay pipe, the kiln-fired ceramic that built the drainage systems of every major civilization on Earth, and how the plastics industry buried it in a single generation. In the shadowed ruins of ancient Nippur, archaeologists brush away centuries of Earth to reveal the first engineered solution to urban waste. Beneath the Temple of Bel, fired clay pipes run in silent lines, their bell and spigot joints locked together with a precision that speaks of deliberate design. These are not simple ditches or chance arrangements. They are modules, T-joints, elbows, straight runs, shaped by hand, fired in kilns reaching nearly 800 degrees Celsius, and set beneath the temple floors to carry away water and refuse. Radiocarbon analysis of organic residue on the bitumen seals places their installation at the dawn of the 3rd millennium BCE during the early dynastic period. The clay itself tells a story. Petrographic thin sections reveal fine silt and scattered quartz grains, the signature of alluvial soils gathered from the Euphrates plain. Each pipe, about 15 centimeters in diameter, was crafted to interlock, forming a continuous conduit through the temple's foundations. At critical junctions, T-shaped fittings direct the flow outward to soak pits beyond the sacred precincts. This was not improvisation. It was urban engineering, born from necessity in a city where stagnant water meant disease. Farther east, the Indus Valley cities of Mohenjo-Daro and Harappa pushed the concept further. By 2500 BCE, fired clay drains are standardized, mass-produced in workshops, and laid beneath gridded streets. Archaeological plans show a vast network, rectangular conduits, 30 by 15 centimeters, with smooth, glazed interiors produced by limestone flux. Thermoluminescence dating confirms their age. Here, bell and spigot joints and 45-degree elbows distribute wastewater from household latrines to main collector channels, all sloped carefully to maintain flow. The system endures, layer upon layer of later occupation, reusing and repairing the same clay lines. In these early cities, fired clay becomes more than a building material. It is the backbone of sanitation, enabling dense populations to thrive. The modularity, the standardization, the very logic of replaceable sections, these precedents echo across millennia. The lineage begins here, in the mud and fire of the world's first engineered drains. In Rome, the story of durable drainage takes on a monumental scale. The Cloaca Maxima, begun in the 6th century BCE, still courses beneath the city's streets. Early phases were little more than stone-lined trenches, but by the late Republic, Roman engineers lined the main channel with fired brick and clay conduits, some over a meter wide. These bricks, kiln-fired to nearly 1,000 degrees Celsius, display a semi-glazed surface, evidence of partial vitrification achieved centuries before the term existed. Each section joined the next with a recessed bell and spigot system. At critical joints, lead-filled mortar sealed the gaps, locking the modular segments together. T-shaped junctions and curved elbows allowed side drains to merge, adapting the system to the city's tangled topography. Imperial maintenance records and archaeological surveys confirm repairs and relining as late as the 9th century CE, but the original fabric endures. After 2,000 years, sections of the Cloaca Maxima remain structurally sound, bearing the weight of city life above. Across the Atlantic, the same logic reappears in the young United States. In 1815, Washington, D.C. installed its first vitrified clay sewer beneath Pennsylvania Avenue. Local brickworks fired the pipe at temperatures exceeding 1,000 degrees Celsius, producing a glossy, watertight finish. The pipe measured 20 centimeters in diameter, with bell and spigot sockets and standardized T-pieces for branch lines. City engineering journals of the period described the pipe as vitrified, a mark of prestige and performance, echoing the Roman tradition. Municipal records show that by the mid-19th century, vitrified clay had become the default for urban sewers throughout the Northeast and Midwest. Portions of the 1815 line still survive in the basement of the old patent office building, a silent witness to the material's staying power. From the cloistered vaults of Rome to the mapped grids of early Washington, the same principles repeat: high-fired clay, modular assembly, and joints sealed for permanence. The lineage is unbroken. Municipal archives and archaeological remains trace a continuous practice, one that links the engineers of antiquity with the city builders of a new republic. The question is not whether clay could last, but why a material with such a record would ever be replaced. Inside the kiln, the transformation begins. A blend of clay and shale, extruded into pipe form, is fired at temperatures surpassing 2,000 degrees Fahrenheit, over 1,100 degrees Celsius. At this intensity, the silica and alumina in the clay partially melt, fusing into a glassy matrix. The process is neither guesswork nor art. It is controlled by modern tunnel kilns that hold temperature to within 5 degrees, ensuring every section vitrifies evenly from end to end. The result is a ceramic so dense it absorbs less than 2% water by weight, with a surface that shrugs off acids, salts, and sewer gases. Laboratory tests confirm what the ancients intuited by trial and error. Under the ASTM standard C700, standard-strength vitrified clay pipe must withstand a minimum compressive strength of 18,000 pounds per square inch. Extra strength grades push past 30,000 pounds per square inch. When tested for load bearing, a 12-inch diameter pipe can support up to 2,600 pounds per linear foot, though modern standards tie this value to bedding and soil strength, not a fixed number. These figures are not theoretical. They are measured, repeated, and published in engineering tables. The material's hardness, often cited as 9 on the Mohs scale, is more conservatively placed between 6 and 7 by micro-indentation, still harder than steel, and rivaling most natural stone. Joint assemblies are subjected to shear loads of 4,250 pounds, simulating the shifting and settling of real-world installations. The glazed surface resists abrasion from high-pressure jetting, a test that gouges plastic but leaves clay untouched. Chemical resistance is measured in sulfuric acid baths, with no measurable mass loss after 30 days in a 5% solution. The numbers are stark. Where other materials soften, corrode, or deform, vitrified clay holds its form. These are not claims. They are the baseline expectations for a pipe that must endure beneath city streets for centuries. The evidence is in the data, not the anecdotes. A sewer main buried beneath a city block in the late 19th century is not supposed to last into the 21st. Yet when municipal engineers lower a CCTV crawler into vitrified clay lines laid in the 1880s, the camera records not rot or collapse, but pipe walls as clean and unbroken as the day they left the kiln. This is not an isolated case. In a peer-reviewed study published in Engineering Failure Analysis, researchers documented vitrified clay sewers in service for 130 to 142 years. Their assessment drew from hours of inspection footage, bell and spigot joints still tight, glazed interiors still smooth, not a trace of corrosion or acid etching. The report's verdict is clear. Deterioration in properly installed vitrified clay is not a function of age. The material is immune to the slow decay that claims iron, concrete, or plastic. Chemical inertness is not a marketing slogan. In the same study, field samples exposed for over a century to domestic sewage and industrial effluent showed no measurable loss of mass. Sulfuric acid, the bane of concrete and metal, leaves vitrified clay untouched. The glassy ceramic matrix, formed at over 2,000 degrees Fahrenheit, is simply not reactive. Engineers have confirmed this in laboratory acid baths and in real-world sewers alike. After decades of exposure, the pipe's composition is unchanged, a fact visible in every cross-section and confirmed by every CCTV run. This is not anecdote or nostalgia. It is field evidence that the numbers from the lab, compressive strength, acid resistance, hardness, translate into century-long service in the ground. The proof is in the footage and the physical record. Vitrified clay does not degrade on schedule. It outlasts the codes, the builders, and the expectations of every era that tried to replace it. Across the American landscape of the late 19th and early 20th centuries, the kiln was as common as the water tower. By 1920, the U.S. Census of Manufactures listed more than 350 clay pipe factories operating nationwide, from the banks of the Ohio to the far edge of California's Central Valley. Each relied on local clay deposits, fueling small-town economies and feeding a growing web of municipal infrastructure. In Ohio alone, state industrial directories from 1905 record 29 independent vitrified clay pipeworks, their kilns firing day and night to meet demand from expanding cities and rural districts alike. The scale was staggering. Annual production volumes in the 1930s exceeded 250 million linear feet, enough to circle the globe nearly twice. Municipal procurement records from Chicago, Detroit, and St. Louis reveal contracts specifying tens of thousands of feet at a time, with delivery schedules tied to the pace of streetcar expansion and new residential plats. City engineering manuals of the era, such as the 1928 Standard Specifications for Sewer Construction, mandated vitrified clay for all gravity sewers, with detailed tables linking pipe diameter, wall thickness, and minimum compressive strength to local soil conditions. This was not a single factory monopoly. Hundreds of small and mid-sized producers competed on price, quality, and delivery, their catalogs filled with bell and spigot joints, T-fittings, and elbows tailored for every possible alignment. The kiln economy was an ecosystem, with clay miners, molders, kiln operators, carters, and inspectors all playing a role. The material supply chain ran deep, binding regional geology to the daily work of city engineers and builders. Vitrified clay was not an alternative. It was the standard, entrenched by specification, habit, and sheer local capacity. Open a city engineering manual from 1938, and the language is unambiguous. All gravity sewers shall be constructed of vitrified clay pipe, extra strength, in accordance with ASTEMC 700. The specification tables run page after page, diameters from 6 to 36 inches, wall thicknesses, minimum compressive strengths, joint details. Each line assumes vitrified clay as the default, not the exception. Municipal procurement records from Chicago and Detroit list contracts for tens of thousands of feet at a time, delivered by rail from local kilns. In St. Louis, city engineers required every pipe section to bear an inspector's stamp before it left the yard. Routine maintenance was not an afterthought. Inspection logs from the 1940s detail annual flushing with high-pressure water, debris removal by hand, and joint checks for infiltration. The glazed ceramic surface resisted the scouring action of cleaning nozzles, a fact noted in city reports. No observable wear after repeated jetting. When a section failed, rarely and almost always from ground movement rather than age, replacement involved lifting a single bell and spigot joint and inserting a new length, matched by catalog number to the original. Archival spec sheets from New York, Cleveland, and Los Angeles all repeat the same language. Vitrified clay pipe to be laid on compacted sand bedding, joints caulked and sealed, minimum cover as per Table 4. The culture of maintenance was built around longevity. Crews expected to inspect, clean, and, if necessary, repair clay mains for generations. The daily work of city sanitation depended on a material whose failure rate was measured in fractions of a percent per year. Before plastic, this was the operational norm. The scale of the coming shift would upend not just materials, but the entire logic of municipal maintenance. PVC did not simply appear on the market. It arrived with a business plan. In 1954, Phillips Petroleum launched Ferro PVC, the first commercial plastic drain waste vent pipe. Within a decade, the language of building codes began to shift. ASTMC 495, adopted in 1960, set a national benchmark for PVC, while the International Plumbing Code and the Uniform Plumbing Code rewrote their standards to include plastic and quietly sidelined clay. A procurement analyst for a major Midwestern city remembers the change as abrupt. The specification sheets came in the mail. Clay was gone. PVC was the new default. Municipal archives from the late 1960s show entire sections of code revised in a single printing. Vitrified clay pipe was replaced by PVC or ABS in every table, every joint detail, every lateral connection. By 1980, the Uniform Plumbing Code had removed explicit allowances for clay in residential laterals under 6 inches. The rewrite was not technical. It was economic. PVC offered a lower upfront price, lighter shipping, and faster installation. Manufacturers flooded the market with fittings, couplings, and solvent cements. Distributors shifted inventory overnight. In procurement records from Chicago, Detroit, and Los Angeles, the same pattern repeats. Clay orders disappear, replaced by plastic. The analyst describes the pressure. If you specified clay, you had to justify it. PVC was assumed to be better because it was new and cheaper. Within 10 years, a material used for 2,000 years was erased from the institutional memory of city engineering offices. The code change was not just a line in a manual, it was the end of a supply chain, a curriculum, and a culture of permanence. The speed of the shift left little time for debate. The replacement cycle had begun. Inside a union training hall, the curriculum tells the story. Apprentices once spent weeks mastering bell and spigot clay joints, learning to set bedding, align T-fittings, and seal every socket by hand. Now, the schedule reads differently. The 2022 National Plumbing Apprenticeship Survey reports that over 80% of programs devote 0 hours to clay pipe installation. The old skills, gravity alignment, clay bedding, the touch required to seat a ceramic joint without fracture, are gone from the syllabus. In their place, solvent welding, plastic couplings, the fast rhythm of PVC assembly. An apprenticeship representative remembers the change as a closure, not a transition. We stopped teaching clay because no one ordered it. The books disappeared. The suppliers stopped stocking fittings. You cannot teach what you cannot source. The erasure was not accidental. As plastic swept through the market, the business of plumbing reoriented itself around speed and turnover. The $70 billion PVC market, projected to cross $100 billion by the early 2030s, thrives on the promise of replacement. Every pipe that fails on schedule is another sale, another installation, another required skill set. Trade manuals from the 1970s still carried pages on clay, joint diagrams, bedding requirements, repair techniques. By the late 1980s, new editions had cut those chapters entirely. Union locals, pressured to keep up with changing codes and supply chains, retooled their training to match the new default. The feedback loop was set as fewer installers knew clay, fewer projects specified it. As demand dropped, manufacturers shuttered kilns, and the supply chain for fittings and repair parts collapsed. This is not just a shift in materials, it is a break in the chain of knowledge. The skills that built infrastructure to last centuries were written out of the curriculum, replaced by the logic of planned replacement. The result is irreversible. A generation of builders no longer knows that anything more permanent was ever possible. Today, vitrified clay still lines the sewers beneath New York, a material engineered for centuries, abandoned in homes for plastic that lasts decades at best. As planned obsolescence becomes code, permanence is written out of our built world. The loss is not just technical, it is a quiet erasure of wisdom, traded for convenience. What else have we been taught to forget? Share your perspective in the comments below.